Integration of rational functions by partial fractions. So hopefully you've heard of this concept of partial fractions, possibly in your pre-calculus course. So now we're going to see how we can integrate certain rational functions by using partial fraction decompositions. All right, so here's the big idea of this section. Notice that 1 over x plus 5 plus 3 over x plus 2, right, to add those fractions we have to find a common denominator, which would be x plus 5 times x plus 2. We build up each of the fractions appropriately. So that's where this x plus 2 comes from. Right, I'd have to build up the first fraction with a factor of x plus 2. And I'd have to build up the second fraction with a factor of x plus 5. That gives me a common denominator, and now I can add the fractions together, and after simplification we end up with 4x plus 19 over x plus 5 times x plus 2. So here's what we're going to do with that. If we were asked to integrate 4x plus 19 over x plus 5 times x plus 2, we have to figure out a way to get that integral, to get that integrand, I should say, the 4x plus 19 over x plus 5 by x plus 2, we need to get that back to 1 over x plus 5 plus 3 over x plus 2. Because if we can do that, then the integral is simple. Because now that's just the integral of 1 over x plus 5 dx plus 3 times the integral of 1 over x plus 2 dx, and those are both natural logs. And so then that's natural log absolute x plus 5 plus 3 times the natural log absolute x plus 2 plus a constant. Now the question is, of course, how to get there. All right, so to create partial fractions, the goal, right, if we're integrating functions of the form f of x is equal to p of x over q of x, where those are both polynomials, right? Those are both polynomials. First, if the degree of the numerator is greater than the degree of the denominator, greater than or equal to the degree of the denominator, we're going to use long division first. We want the degree of the numerator to be less than the degree of the denominator. We factor the denominator as much as possible. We want to get the denominator in terms of factors of the form ax plus b or ax plus bx plus c. That cannot be factored any further. Finally, we're going to express the proper rational function as a sum of partial fractions. Now it gets broken down even further. There's several different cases that we have to consider. The first case, if the denominator is a product of distinct linear factors. So we don't have any factors that are being squared in the denominator, and they're all linear. All right, and if that happens, if we only have linear factors in the denominator and they're not distinct, then we can write the rational function as a1 over a1x plus b1 plus a2 over a2x plus b2, etc. Now what does that mean? Okay, look. We have this integral of x over 2x squared plus 7x plus 4. So notice that x over 2x squared plus 7x plus minus 4. That denominator can be factored as 2x minus 1 by x plus 4. If you need to review factoring, that's something you're going to have to do on your own. All right, now, so what this says, notice that each of these is, right, these are both linear factors and they're distinct, right? They're different from each other. So what that means is I can write x over 2x minus 1 by x plus 4 as, I'm going to write this as a over 2x minus 1 plus b over x plus 4. Now I have to figure out what's the appropriate a and b. Okay, so what we do at this point is we multiply both sides by 2x minus 1 and x plus 4. Now that clears out the entire denominator on the left-hand side, yielding x. On the right-hand side, I would have a times x plus 4 plus b times 2x minus 1. And so then x equals ax plus 4a plus 2bx minus b. Now notice, let me simplify this a little more. So then x would equal, I'm going to group all of the x's together. So on the right hand side, so then I would have a plus 2b times x, and then the constants are 4a minus b. Now that x, if I really wanted to, I could think of that x as a as a 1x plus 0, right? X is equal to 1x plus 0, and that's equal to a plus 2bx plus 4a minus b. And so now, if the left-hand side and the right-hand side are equal, then I must be able to write that a plus 2b equals 1, and that 4a minus b equals 0. And now I have to solve this system of equations. Solving the system of equations for a and b. We're going to use whatever techniques we need, substitutions, eliminations, whatever. So I'm going to use, I noticed that if 4a minus b is 0, then 4a equals b. And so I can substitute into the other equation. And so I have a plus 2 times, instead of b, I can replace it with a 4a equals 1. So what's that? 9a equals 1, and a is 1/9. And so a is 1/9, then b would equal 4 times 1/9, b would equal 4/9. Well, now that was all algebra. Now that we've done all the algebraic work, now we can do the calculus. So, the original integral of x over 2x squared plus 7x minus 4 dx is equal to the integral of a over 2x minus 1 plus b over x plus 4 dx. And we figured out that a was 1/9 and b was 4/9. So then this becomes integral of 1/9 over 2x minus 1 plus 4/9 over x plus 4 dx. And I guess I should have some parentheses or brackets here. And now I can break this up into two integrals. I can write this as 1/9 of the integral of 1 over 2x minus 1 dx plus 4/9 of the integral of 1 over x plus 4 dx. And now these are both going to end up being natural logs. We have to be a little careful. We have to make a u sub here. If I let u equal 2x minus 1, then du is 2 dx. So I need a 2 here and a 1/2 on the outside. But then it's relatively simple. I'd have 1/8 natural log absolute 2x minus 1 plus 4/9 natural log absolute x plus 4 plus a constant. So that's the idea for partial fractions. The only difference is in how we write those fractions in the beginning, and that all depends on what the denominator looks like. Alright, so now let's consider the second case where the denominator is a product of, again, only linear factors, but some of which may be repeated. Okay, so if we have a repeated linear factor, then we're going to have a repeated fraction in a sense. And so let's see how it works. All right, so in this exercise, we have the integral of x squared plus 2x minus 1 over x cubed minus x squared. Notice that this denominator can be factored as x squared times x minus 1. And you say, well, wait a second, that x squared, that's a quadratic factor. That's not linear. Oh, yes, it is linear because it's x being squared, and x is linear. And so that's x times x minus 1. I have a repeated linear factor. Okay, so what that means is x squared plus 2x minus 1 over x squared by x minus 1 can be written as a over x. Linear factor, but wait, I have a repeated linear factor. That x is repeated. So then I have another factor of b over x squared. I should say another term. And then I have another term of c over x minus 1. And now I follow the same process as before. I multiply both sides of the equation by the LCD, which is x squared by x minus 1. Multiply both sides by x squared times x minus 1. The left-hand side, everything cancels out in the numerator and denominator, or I should say those factors cancel out. I get x squared plus 2x minus 1. On the right-hand side, I have the x squared by x minus 1 times x. So I'd have a times x minus 1. From the second term, I'd have b times x minus 1. And from the third term, I'd have c times x squared. So the right-hand side becomes ax squared minus ax plus bx minus b plus cx squared. Combining the like terms, I'd have a plus c times x squared plus negative a plus b times x minus b. And so that's 1x squared plus 2x minus 1. And so now we can write the system of equations we need to solve. Equating the square terms, a plus c must equal 1. Equating the x terms, negative a plus b must equal 2. And equating the constants, negative b must equal negative 1. And so now I have to solve this system of equations. And this was actually fairly simple to solve. If negative b is equal to negative 1, that implies that b is 1. If b is 1, substituting up into the second equation, negative a plus 1 equals 2. And so then a would equal negative 1. And then substituting that up into the first equation, negative 1 plus c equals 1, c would equal 2. So there's the algebra, and now the calculus. We were asked to integrate x squared plus 2x minus 1 over x cubed minus x squared dx. And we said, well, we can write that as the integral of a over x plus b over x squared plus c over x minus 1 dx. We solved for a, b, and c. So this then becomes the integral of negative 1 over x plus 1 over x squared plus 2 over x minus 1 dx. And now I can integrate this. And these are all fairly simple, but if we wanted to, we could split this up into 3 integrals. So let's see, I can bring that negative outside. Negative integral x to the negative first plus integral x to the negative second plus 2 times the integral of 1 over x minus 1. And I've been forgetting my dx's. Sorry about that. So then this becomes negative The integral of x to the negative first, that's natural log absolute x. The integral of x to the negative second, that would be minus x to the negative first. And then plus 2 natural log absolute x minus 1 plus a constant. So notice usually the calculus part is fairly simple. It's the algebra that's the difficult part with these exercises. Third case, the denominator contains an irreducible quadratic factor, or possibly quadratic factors. And so when that happens, we'll have a term, when we do the partial fraction decomposition, we'll have a term of the form ax plus b over little ax squared plus little bx plus c. All right, so let's consider this example. We're asked to integrate x squared minus x plus 6 over x cubed plus 3x dx. Notice that this denominator can factor as x by x squared plus 3. And that denominator cannot be factored any further. Right? The x squared plus 3 is irreducible over the real numbers. So, x squared minus x plus 6 over x by x squared plus 3 can be written as a over x, because I have that linear term, and now I have this irreducible quadratic factor, so I would have a term of bx plus c over x squared plus 3. All right, now, as before, we multiply both sides of the equation by the denominator, x by x squared plus 3. Everything cancels out over on the left-hand side. And so I would have x squared minus x plus 6. Now on the right-hand side, I would have a by x squared minus plus 3. And then I'd have bx plus c times x. Distributing on the right-hand side, I'd have an ax squared, a 3a, a bx squared, and a cx. Grouping, I'd have a plus b times x squared plus cx plus 3a, and that must be equal to x squared minus x plus 6. So then, matching the like terms, a plus b must equal 1. Those are the x squares. The linear terms. C must equal negative 1. And then 3a must equal 6. All right, so if 3a equals 6, then a equals 2. And if a plus b is 1, then 2 plus b is 1, and b is negative 1. So, the integral of x squared minus x plus 6 over x cubed plus 3x dx is equal to the integral of a over x plus bx plus c over x squared plus 3 dx. And so this then becomes the integral of 2 over x plus negative x minus 1 over x squared plus 3 dx, because b was negative 1 and c was negative 1. I can break this up. So I'm going to write this as the integral of 2 times 1 over x dx. Now I've got that negative x minus 1. I'm going to write that as, I'm going to break up that fraction into its two fractions. I would have, so what's happening here is I'm going to take this fraction and I'm going to break that up as negative x over x squared plus 3 minus 1 over x squared plus 3. All right, so that becomes minus the integral of x over x squared plus 3 dx minus the integral of 1 over x cubed plus 3. I'm sorry, x squared plus 3 dx. All right, and now we can integrate these. On this, the first term's fairly simple. That's just a straightforward natural log. 2 natural log absolute x. Now the second term, we need a u sub. I'm going to let u equal x squared plus 3, then du is equal to 2x. So I need a 2 here and a 1/2 outside. And now it's a natural log. So minus 1/2 natural log absolute of x squared plus 3. Now the third integral is an arctangent. So notice that that's the same as 1 over x squared plus root 3 square. And so then that tells me arctangent. So this becomes then minus 1 over the square root of 3 arctangent of x over the square root of 3, and then plus the constant. All right, so we had to use a little bit of memorization on that one. We had to recognize that general form. The fourth case is what happens if we have repeated irreducible quadratic factors. So if we consider this exercise where we have x cubed plus 2x squared plus 3x minus 2 over x squared plus 2x plus 2 squared. This x squared plus 2x plus 2 is irreducible over the real numbers. We can't factor it any further. So what we would then say is that this x cubed plus 2x squared plus 3x minus 2 over x squared plus 2x plus 2 squared can be written as an ax plus b over x squared plus 2x plus 2 plus a cx plus d over the x squared plus 2x plus 2 squared. All right, and then we would multiply both sides by the x squared plus 2x plus 2 squared, yielding x cubed plus 2x squared plus 3x minus 2. Now, in the first term, I'd have an ax plus b, and only one of the factors reduces out, so times x squared plus 2x plus 2, and then I'd have a plus cx plus d. Alright, so this is a little messy. I'm not going to go much further with this. If you feel like solving this system, you should find that a equals 1, b equals 0, c equals 1, and d equals negative 2. And so then we could integrate very carefully. This would be a fairly difficult integral to evaluate. We're not going to actually go through with it. I'm not going to ask you to do one like this on the test. So I just wanted to at least introduce the concept to you. Alright, so now let's use some of these ideas. Let's consider the integral of from 0 to 1 of x cubed minus 4x minus 10 over x squared minus x minus 6. So first, notice that the degree of the numerator is greater than the degree of the denominator. So we're first going to use long division to put this in a different form. Alright, so using some long division, x squared minus x minus 6 divides into x cubed minus 4, oh wait a second, there's a no square term, so I add in a 0x squared minus 4x minus 10. Alright, long division, x squared divides into x cubed, x times, multiplying back, x cubed minus x squared minus 6x, subtracting that line. There go the x cubes. 0 minus negative 1, that would be plus 1x squared plus 2x. Bring down the minus 10, repeat the process. X squared divides into x squared one time, multiplying through. That's a 1x squared, a minus x, and a minus 6. Subtracting gives us a 3x and a minus 4. All right, so this integral becomes then the integral 0 to 1 of x plus 1 plus 3x minus 4 over x squared minus x minus 6 dx. All right, so now I'm going to focus on the 3x minus 4 over x squared minus x minus 6. So 3x minus 4 over x squared minus x minus 6 can be written as, well, let's see, x squared minus x minus 6 factors as x plus 2 by x minus 3. So then I can write this as a over x plus 2 plus b over x minus 3. Multiplying through by the denominators gives 3x minus 4 is equal to ax minus 3a plus bx plus 2b. Grouping together, then a plus b must equal 3, and negative 3a plus 2b must equal negative 4. Solving this system of equations using what we've learned in algebra, we find that a is 2 and b is 1. Sorry, a is 2 and b is 1. So then so on our integral becomes the integral from 0 to 1 of x plus 1 plus 2 over x plus 2 plus 1 over x minus 3 dx. All right, so now these are all fairly simple integrals. And so this becomes 1/2 x squared plus x plus 2 natural log absolute x plus 2 plus natural log absolute x minus 3, and that's evaluated from 0 to 1. All right, evaluating at 1, that would be 1/2 of 1 squared, so that would be 1/2 plus 1 plus 2 natural log of 1 plus 2 is 3, plus the natural log of 1 minus 3 is negative 2. The absolute value of negative 2 is 2. So plus natural log of 2. Subtract. Now substituting 0. 0 plus 0 plus 2 natural log 2 plus natural log 3. Combining the like terms, let's see, I would have 1/2 plus 1, that's 3/2. I have 2 natural log 3 minus natural log 3, so that would be plus a natural log 3, plus a natural log 2 minus 2 natural log 2, so that would be minus natural log 2. And now I can group these together, the natural log of 3 minus the natural log of 2. So let's see, that would then be equal to 3/2 plus the natural log of 3/2. Now let's consider the integral of dx over 2 times the square root of x plus 3 plus x. Now, this doesn't look like what we have been talking about in this section. But what we're going to see is sometimes we can make a substitution and turn this integrand, I'm going to turn this integrand into a rational expression, and then I'll be able to use partial fractions. All right, so if I look at this, this doesn't seem to fit anything that we've done before. So I'm going to try a substitution. I'm going to let u equal the square root of x plus 3. Well then, I could find the du from here, but what if I now work with this a little bit? If u is the square root of x plus 3, then isn't u square x plus 3? And so then, notice then that the x would then be equal to u squared minus 3. And then dx would be 2u du. Alright, so after we make that substitution, then I would have the integral of 2u du is equal to 2u plus u squared minus 3. Which, if we clean this up a little bit, that's then the integral of, let's see, 2u over u squared plus 2u minus 3 du. Well, now wait a second. Now that looks rational in terms of u. Alright, so let's see. 2u over, now u squared plus 2u minus 3, that factors as u plus 3 by u minus 1. So now I'm going to use partial fractions decomposition. That would be then a over u plus 3 plus b over u minus 1. Multiplying through, I get 2u is equal to a times u minus 1 plus b times u plus 3. Oh, and so let's see, that would be au minus a plus bu plus 3b. All right, so now I have a system of equations I can solve. So then a plus b must equal 2, and negative a plus 3b must equal 0. And if we solve this system of equations, it's actually not too difficult. We should find that a is equal to 3/2 and b is equal to 1/2. So then my integral, get a little bit more room here, my integral becomes then, wait a second, I made a substitution. Oh, I didn't. This wasn't definite. I was thinking this was a definite integral, and I didn't change the limits on integration. This is indefinite, so not a problem. All right, so we're going to now write this as the integral. Let's see, a over x plus 3, so that would be 3/2 over x plus 3, u plus 3, excuse me, plus 1/2 over u minus 1. And this would then be a du. We can now integrate. So this would be 3/2 natural log absolute u plus 3 plus 1/2 natural log absolute u minus 1 plus our constant from integration. And now we substitute back. U was the square root of x plus 3. So then I'd have 3/2 natural log of square root of x plus 3 plus 3 plus 1/2 natural log absolute square root of x plus 3 minus 1 plus a constant. So even though our original expression, our original integrand, didn't look rational, through an appropriate substitution, we could turn it into a rational integrand and use partial fractions decomposition to evaluate the integral. All right, that concludes this presentation.